Hello and welcome to the second Core Pure Maths video on volumes of revolution. And this time we're going to look at a modelling question. So volumes of revolution can be used for modelling problems from real life. And examples of that often include things to do with bottles or containers. In this case, we're looking at a design for a pen. So try to picture the situation because that can really help you understand what's going on. A manufacturer wants to cast a prototype for a new design for a pen barrel out of solid resin. So we're looking at something like a Bic biro, and we're looking for to model the casing here for the biro. So we've got a suggested model here using using the equation y equals k minus 100 x squared. Let's just write that slightly more clearly in case you can't see over the video. But y equals k minus 100 x squared. You'll be given that equation in the question. This region is bounded by the x-axis and the curve, and it's going to be rotated about the y-axis. So we're rotating this section of the curve around the y-axis, and each unit on the coordinate axis represents 1 centimetre. So just double check any scale in case you have to convert units at the end of the question. Now it says, suggest a suitable value for k. So this is supposed to be a pen. So if I look at my pen here, we might say it's somewhere between 12 centimetres, maybe 12 centimetres would be about here, and 15 centimetres. So you can choose your value of k, but I think any value of k between 10 and 15 would be a reasonable value to take. I'm actually going to take k equals 14. So we've got a suitable value of k, then it says use your value of k to estimate the volume of resin needed for the prototype. So we're going to say that the volume of resin needed is going to be pi x squared, pi times the integral of x squared dy, because we're rotating about the y-axis. So then we substitute in our values for the k that we've used and the function we're using here, and this is going to be pi, so x squared. We need to rearrange this equation here. So we've got here the equation y equals 14 minus 100 x squared. So if I want to know what x squared is, it's going to be 14 minus y over 100. So that's just rearranging this equation here to get 14 minus y over 100 is equal to x squared. And I'm going to integrate that with respect to y. I need to think what limits I'm going to use. This top limit here is going to be the height of the pen, which is going to be 14. And the bottom limit is going to be 0 because this is where we're going to rotate it about. So now we get on to doing the actual integration. This is equal to pi. I'm going to take my 100 out of this expression here, and I'm left with 14y minus y squared over 2, and I'm going to evaluate that between 14 and 0. So make it clear that you are using the limits correctly. So this is going to be 14 times 14 minus 14 squared over 2. Take away 0, because when I substitute 0 into there, that's what I get. And that is equal to 49 over 50 pi, but we wouldn't leave it like that. We would give it as a value. That's equal to 3.0772. And the units, always very important in a modelling question, centimetres cubed. We might decide that's maybe a bit too accurate to give it like that, so maybe we'll go with 3 significant figures, 3.08 centimetres cubed to 3 significant figures. Now, the last part of the question says, state one limitation of the model. So one thing about the model that's not going to work out quite right. A couple of things you could say here. A limitation is it does not consider the wasted resin. So it's unlikely in a manufacturing process that you wouldn't waste any of resin at all. So you could say for a limitation, it does not consider any wasted resin. The other thing it doesn't consider is that there would be space inside the pen for the ink. Okay, so the other thing you might put is likely to be space inside the pen for the ink. In fact, you could be stronger than that because it's not likely to be. There would have to be space inside for the ink. So those are two of the comments you could have put there. So you've got to look carefully at what's rotated here. Also, bear in mind for these questions, you can have, and often do have, questions made up of sections. So you might have a vase, for instance, that's made up of a straight line and a line or a curve like that being rotated to create this vase here. And if you did that, you might have two sections to your volume. So you might have to work out a volume for the top section and a volume for the bottom section and add them together. And you might need to use a formula for the area of a cylinder, the bottom here. You wouldn't have to do integration for that. You could just use the volume of the cylinder for that bottom section. So you need to draw a diagram for the separate parts for this and then add them together.